To better understand powers, we need to understand a couple of basic vocabulary terms that are very, very essential, namely the word power. A power is the product of multiplying a value by itself. When we talk about powers, exponents, etc., power is the whole thing. It's the exponent, it's the big number, it's any negatives. That's the whole piece. And we'll talk about the anatomy of a power in a moment. The base is the value that you are multiplying by itself. This is also the big number in the power. An exponent tells you how many times you are multiplying the base by itself. This you might know as the smaller value. Let's apply that vocabulary to an actual power. A power is made up of a base and an exponent. So look at the example down below. 2 to the third power, or 2 cubed. The base is the large value, so 2 is our base. It's very important that you know what's your base and what's your exponent, because they each have special roles when we try to evaluate powers. The exponent is the superscript value in the upper right-hand corner. That means it's the small value that's moved up. Notice that these two numbers do not look the same. Your base looks like every other number that's going to be in your algebraic expression, whereas the exponent is smaller and up in the corner. The base, just like the base of a house, is the foundation. It's at the bottom. It touches the ground. It holds up that exponent. Altogether, we call that a power. Answer a little think, pair, share to the right. 3 to the second power and 2 to the third power. Are these the same powers? In your own words, explain why or why not. Powers came about because we were tired of multiplying over and over to get particularly large or dividing down to get particularly small values. So, because they're related, to evaluate a power, write a repeated multiplication expression. You do this by looking at the base and the exponent. Remember, knowing what your base and what your exponent is will really help you. Multiply the base by itself as many times as the exponent tells you to. In the example below, 2 to the third power, or 2 cubed, we have 2 as our base because it's the bigger number, it's the meatier number, it's down at the bottom. 3 is our exponent. It's that superscript number. It's up in the right-hand corner. It's smaller. So I'm going to write out 2 times itself 3 times. Notice I'm not doing 2 plus 3. This is a warning. Do not multiply 2 times 3. That's one of the most common errors. So now I have to evaluate 2 times 2 times 2. This is a great little calculator moment here. 4 times 2 gives me 8 as my final answer. Again, this is so we can understand in a world without a calculator how to evaluate. Challenge yourself to do the work and then go through and use a calculator moment. Most calculators will have what's called a caret button. Let's try a couple more examples. 5 to the third power. 5 is our base. 3 is our exponent. Remember, the base tells you what to multiply. The exponent tells you how many times. So I'm going to multiply 5 by itself 3 times. Notice I'm not multiplying 5 times 3. I'm multiplying 5 by itself 3 times. 5 times 5 gives me 25. 25 times 5 gives me 125. Again, whether you write it out and do the repeated multiplication or go straight to your calculator, this is a great opportunity for a calculator moment. But take the time, show your work, plan it out. On your own, try the next problem. There are 3 special cases worth mentioning when evaluating powers, mostly because by being aware of the base and the exponent, you may not have to actually evaluate these answers. In many cases, they tell you exactly what the answer will be. Special case number 1. All powers that have 0 as an exponent equal 1 automatically. Let's look at why that is. So let's take x to the third, for example. X to the third, my base is x, my exponent is 3, so I'm multiplying x by itself 3 times. If I look at x squared, or x to the second power, that's x times itself 2 times. To go from 3x's multiplied together to 2x's multiplied together, we had to divide by x. Likewise, if we went from 3 to 2 to 1, we'd have to divide by x again. If I divide x by x, I'm going to get 1. Anything divided by itself equals 1. The second special case, all powers that have 1 as an exponent are equal to the base. This is pretty self-explanatory. If your base is x or 5 or 30, the base is what's being multiplied. The exponent tells you how many times. Well, if the exponent's 1, you're just going to write whatever the base is 1 time. So x to the first is x. 5 to the first is 5. 30 to the first is 30. This is what we would call one of those invisible ones of math. 5 to the first could be written, but you rarely would see it. You would more or less likely see it written as 5. The third special case, all powers that have 1 as a base equal 1. Again, very easy to visualize. If I have 1 to the third power, 1's my base, that's what I'm multiplying. I'm multiplying it by itself 3 times because my exponent is 3. 1 times 1 is 1. 1 times 1 is still 1. I could multiply 1 together as many times as I'd like, and I'd always get 1. As with anything in math, as soon as negatives join the game, things get complicated. There are a couple scenarios where negatives can really throw you off. This is when your base is negative and when your power as a whole is negative. Negative exponents we'll cover in a much later lesson. So with negative bases, if the base and negative sign are contained inside a set of parentheses, then the base is negative. So I think of it in terms of a fishbowl. Inside your fishbowl, you have your fish, you have some sand, you have water, maybe a little fun castle. But if you pick up that fishbowl and carry it around, all of it goes with you. The fish, the castle, the sand. When you pick up or interact with those parentheses, everything goes with it. The 4, the negative. So my base is negative 4 in the example below. If the exponent is odd, the answer will be negative. If the exponent is even, the answer is positive. Now we know that exponents and powers are related to multiplication. This is the same rule we saw in multiplication. When you multiply together an odd number of negative values, you get a negative answer. When you multiply together an even number of negative values, you get a positive answer. So my base in the example below is negative 4. So I'm going to multiply negative 4 times itself 4 times. Negative 4 times negative 4 times negative 4 times negative 4. Looking at this, there's a couple things that pop out. My exponent is even. So, based on my rules, my answer should end up being positive. When I write it out as repeated multiplication, I see that I have an even number of negative values. So I'm going to multiply them all together. Or again, this is a great calculator moment, but we're going to take the time to challenge ourselves and plan out our work. Negative 4 times negative 4 gives me 16. The other negative 4 times negative 4 gives me 16. Again, when I multiply even negatives together, I get positive. 16 times 16 gives me 256, and I've already established that it's positive. So my answer is correct. Had I come out with a negative answer, I would want to go double check my work, because at the very beginning, I predicted, based on my knowledge of exponents and powers, that this would be a positive answer. Let's try another example together. Negative 3 to the third power. Well, my base is negative 3 because that negative and the value 3 are all together in that set of parentheses. That is my base. That is my fishbowl. So I'm going to take negative 3 times itself 3 times. Again, I could take the time to look at my multiplication rules. I see an odd number of negatives, so my answer is going to be negative. My exponent was odd with a negative base, so I know going into this, my answer will be negative. So again, this is a great calculator moment, but let's take the work. Negative 3 times negative 3. If I multiply those first two together, I get positive 9. Two negatives make a positive when I multiply them together. 9 times negative 3 is going to give me negative 27, which fits my prediction of a negative answer. On your own, try number 2. When the whole power is negative, it looks very similar to when the base is negative. And this is where students and adults and politicians, everyone, makes mistakes. So let's look. If the power has a negative sign, but it is not contained inside of a parentheses, then the whole power is negative. We no longer have a fishbowl. Our fish is flopping around on the table, the water spilled everywhere, and I don't even know what happened to the castle anymore. The answer is always, 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 always negative in this case. My base is positive, but my answer will be negative. Another way to look at it is, what does the exponent directly interact with? In this case, negative 4 to the 4th power. The exponent is only touching the positive 4 base. That negative is out by itself. So when I rewrite it, my base is 4, so I'm going to multiply positive 4 times itself 4 times. I still know that my answer, no matter what, is negative. So if I'm showing my work, instead of taking a calculator moment, I'm going to put that negative in there somehow. You can either put brackets or you can multiply the whole problem by negative 1. But you want to make sure that that negative follows through. Inside the brackets or parentheses, I have 4 times 4 times 4 times 4. Well, that's 16 times 16. But again, that negative is still there. 16 times 16 was 256, but my answer is going to be negative. Compare this negative 4 to the 4th to the other example of negative 4 to the 4th. The base is not the same. We have a positive base here, but my negative carries through all the way to the answer. Same thing with example number 1. My base is 3. It's not inside a fishbowl, so that exponent can only affect the 3. That negative is just out by itself, telling you that the whole power, the whole evaluated answer will be negative. So my base is still 3. I'm going to multiply 3 by itself 3 times. But keep in mind that negative's still there, whether you want to use parentheses or multiply by a negative 1. Inside those parentheses, 3 times 3 is 9. 9 times 3 is 27, but it's going to be negative 27. Now, this is a case where the parenthesed version with negative 3 in parentheses to the 3rd power ended up having the same exact answer. However, these two problems are different. One has a negative base, one is a negative power with a positive base. On your own, give number 2 a try.